Good morning and good afternoon. Before we get started, we have a few housekeeping items that we would like to take care of quickly. We welcome everybody to today's session on Know Your HSS Welds. First, your phone lines are muted for today. Any questions that you might have as we go through the presentation, please do not hesitate to pop them into the questions widget in your GoToWebinar control panel. Feel free to do that during the presentation. There will also be some time at the end of the presentation for us to answer any questions that you pose during the talk. Any questions that we don't get to during our 1 hour time together, I will make sure to contact you individually after today's session, and we can cover those with you offline. So today's webinar will accredit you with 1 PDH hour, and that is for the specific attendee. It cannot be transferred unless you talked with us previous to today. And in order to get a PDH email to you, you must indicate that at the end of the presentation. At the very end, there will be another poll that pops up simply asking you if you'd like a certificate emailed to you or not. When you complete that poll, that's the proof that we need that you attended the webinar and that we will issue you your certificate for your license continuing education credits. If you're self-reporting for today, then you don't need a certificate and you can go ahead and do that on your own. For polling questions, there will be one at the middle of this session today and then one at the end to verify your attendance. Please make sure that your pop-up blocker is disabled. We've had a few issues in the past where that is blocking the poll question. Additionally, if you're in full screen mode, you might need to reduce or minimize that screen so that you can see the polling widget because it might appear behind the slides. And then you can re-enter full screen view after that. If you purchased a site registration and you are all in an office, or if you have people working remotely, an attendance sheet is required. This is available in the handouts widget in the GoToWebinar panel. We need that completed and emailed to Stephanie Fontaine at sfontaine@steeltubeinstitute.org in order for everyone in your group to receive their PDH certificates. If you're licensed in the states of Florida, Maryland, North Carolina, and/or New York, we need your license number to issue your certificate. You're also required to complete a quiz. A link to that quiz will be emailed to you at the end of the webinar, and it must be completed within 24 hours. After you've completed and passed with flying colors, then we'll send that certificate to you. PDH handouts of the slides are in the control panel. You also should have received links to those handouts in your email. Feel free to download those for your use during today's presentation. Lastly, I need to mention in advance that today's webinar is being recorded. We encourage you to visit our website and take advantage of all the valuable information that we have there for you to design HSS. The Steel Tube Institute's goal is to be your trusted resource for all steel tube and pipe products. We have a resource library that documents lots of different HSS topics, capability tool that will help you find availability for HSS products, some design aids such as limit state tables, design manuals, Excel spreadsheets, HSS Connects, which is a software tool, and then these webinars that you are logged into today, e-news blasts, and professional membership options. So with that, it is my pleasure to introduce Kim Olson, Manager of Technical Initiatives at Construction Solutions with Nucor. Her topic for today will be Know Your HSS Welds.
Thank you, Kathleen. Hello, everybody. Good morning and good afternoon. As Kathleen mentioned, today we're going to talk about HSS welds. So what's the big deal? Why do we need to devote a webinar to those welds? They're pretty common, and there are definitely some best practices that will lead to more economical structures and happier fabricators. which in turn leads to happier designers. So we're going to talk through some general considerations, how you actually design those welds, then some considerations that maybe we as designers don't always think about when it comes to the person actually performing the welding. And then we'll touch on AESS at the end of the presentation. This structure that you see here on this slide does have architecturally exposed structural steel in that roof member. We were involved in the connection design for this fabulous structure at Lewis University, thanks to White & Company. As I go through our talk today, I want to first clarify some of the terminology that I may use, as I might bounce around a little bit. When I talk about a branch member, that's what's being connected to the main member. So a branch member could be a plate, or it could be a branch like in the traditional sense in a truss member. Cord members are typically what we're connecting to the main member that is continuous. So for the connection on the left, that would be the column, or again, in a traditional truss, we know what a cord member is. Everything that we're going to talk about today is based on AWS D11, the 2020 version. Clause 10 is the chapter that most of the information is contained in for the tubular welds. So that will be our focus. And then, of course, just a quick review of some abbreviations that you'll see throughout my presentation. SMAW refers to shielded metal arc welding. FCAW, flux cord arc welding, and gas metal arc welding are common welding procedures that you'll see throughout this presentation today. So what's the big deal? Why are we talking about welding to HSS? Well, it's really a different animal than welding to a wide flange section. You can see those stress profiles on the right-hand side. When we're welding across the face of a wide flange section, we have the highest stress at the center of the flange, which happens to correspond nicely with the web that backs it up and stiffens that particular member. However, if you look at the stress profile on the left of the HSS member, our highest stress points are where that HSS wall face is strongest, and that's stiffened on its edges, which corresponds to those side walls. So that leads to some of the discrepancies between welding to wide flange and to HSS, and some of the differences that we're going to point out today. It's not very easy to directly transfer load to sidewalls in most cases, so we really have to take into account the load path when we're looking at these welds. There are some quotes, many quotes have been made. These, I think, are most impactful to me when thinking about HSS welds. Blodgett says, provide a path for the force to enter the part that lies parallel to the force. Well, thinking through that with an HSS, that can be complicated, as the path is most likely to the sidewalls. Dr. Miller says a good welded connection has a clear and direct load path. Again, with an HSS, that can be a little bit difficult. What I love, especially for HSS, and to keep in mind when thinking about welding to HSS, is that dependent on the stiffness of the element, the load path is dependent on the stiffness of the elements in the structural system that Carol Drucker mentioned in a presentation. Very important when we're talking about HSS welding, due to the flexibility of that HSS wall and the uneven load distribution. The quality of the weld starts and stops when we're welding across the face of an HSS is going to be critical. As you can see, those are where the welds are most highly strained. When we're talking about HSS welds, one complication is that we can only weld from one side usually. So that usually will lead to larger weld sizes. Also, what's a little bit unique about HSS connections, as you likely know, is that the member selection or the member thickness is tied to the connection capacity significantly. So that causes some issues in the way that we typically design our connections. Some EORs don't design connections. They will design the member, and then there will be a delegated connection designer that has to take care of the connection part. That leads to issues because often the connection capacity is tied to the member thickness, and therefore when we have the discontinuity between the two parties that are involved in that design, that can lead to some issues. So it's super, super important, and I hope that I'm making my point here. If there's one thing that you remember from today is that the demands on a connection may require the member size to be increased. This is very different than a philosophy we typically follow with open shapes. And it's very important for the person designing the main member to design the member to actually think about the connections as well, even if you aren't the one responsible for designing the final welds, bolts, and plates to it. So there are a few general considerations that I want to talk about as we get started. First is a design philosophy when it comes to sizing welds to HSS members. There are two different design philosophies that have historically been employed. The first at the top of the screen is to develop the yield strength of the plate or the HSS member. So I know that's easy on our drawings. We don't have to think about the forces. We just say develop or design the connection, develop the yield strength of the plate and HSS branch. However, I hope we all recognize that because this is the upper limit, it's very conservative, and in most applications it's not needed. There are some reasons for doing that, but most of them we don't need that. And so it's really not required because it is a very uneconomical way of designing your connections. The second option or way to design your welds is to resist the actual applied force in the plate or in the branch that we're connecting to the HSS member. So this is really where today's presentation is going to focus on, because this is the most economical way to design these connections. And so this is where I want us to kind of pay attention and think about when we're going through these provisions today for welding. Another significant impact is just the geometry of the members as they're coming together, especially when we're talking about tube to tube connections, like you can see here. It could be beam to column, it could be a truss connection, but they all have significant impacts on the cost and the difficulty required to fabricate and weld. With a matched connection on the left-hand side, you can see that would be something like an HSS 6x6 connecting to an HSS 6x6. So equal widths, but you can see that the weld across the face, so that's parallel to your screen, that can be a fillet weld across the face of the HSS. But going in and out of your screen, longitudinally of that cord member, we're going to end up with a flare bevel groove weld, which can be more costly. We don't get as much strength out of something like that. And additionally, you can imagine that the larger the tube that we're connecting to, so really the thicker the tube is, the larger the radius, the corner radius is. 2T is the average for the industry for the corner radius. It's based on the thickness of the tube. So a thicker tube is going to have a larger radius. The larger the radius is, we can run into issues where we're going to need backing, and we'll talk about that in a little bit, which will impact not only our design but the fabrication costs. A step connection is really a better way to go and better thing to think about with your designers and with your architects. This step connection that I show in the middle is really ideal, although you can get a little bit too crazy with the step connection that's shown on the right-hand side. Something like what's shown on the right-hand side is a step connection, which is great for welding. Obviously, that branch member is landing right on the flat of the cord member, so we'll be able to use fillet welds, which are very economical to weld all the way around that member. But you can also envision that this is kind of like having a concentrated load at midspan for that thin HSS wall. So we might not be able to achieve the strength out of that connection that we're looking for. Something more ideal would be what's shown in the middle, where we've got a step connection, so not equal widths, but we're not crazy about it. We've got something that's going to land on approximately the full flat of that face of the HSS. That allows us to use economical fillet welds, but also gets us so that we're delivering the load as close to the sidewalls as possible. So that's really optimal. My point in bringing this up is that I think we as designers have the ability to influence our design professionals that we work with, most likely architects. As an architect, if I put that hat on, which I know is a scary thing, I probably am always going to draw or sketch out a match connection or a truss with equal widths, because that makes a lot of sense and it seems very neat and architecturally pleasing. However, if the element that we're designing here is maybe a roof truss or a bridge over an overpass, where we're looking at it from, you know, a large distance away, I might not be able to tell that that we're looking at a matched connection versus a step connection. And so it may be worth bringing this up to your designers that, hey, there's some significant savings if we can make these branches a little bit more narrow so that they can be welded to the cord members using fillet welds and avoid the complexity of a matched connection. Likewise, I think we can bring up the same topic as designers with K-type connections. So again, K connections as defined by the specification, you more or less have an equivalent load coming in and going out of each branch member that defines a K. There are two different types, gapped versus overlap, and these two types have a very different fabrication costs. Overlap connection, you're typically to end up with a stiffer joint, a stronger joint there. And so we may lend ourselves to that type of connection. It's also great for fatigue. However, think about the logistics of putting that together in the fabrication shop. We've got to, where historically in a gap type connection or other truss type connections, we have some flexibility for fit up. We can tack weld those members together before we perform our final welding to make sure that everything's going to go together easily and adequately. With an overlap connection, I don't really have the ability to do that. I have to make some final welding because one of those toes, the hidden toe, is going to get covered up by another member. So I might need to actually make some final welding before I'm sure that everything's going to go together well and easily. So there's also an accessibility that comes into play of assuring that these welds can be made, and that's why you'll see the user note in the specification with a dihedral angle of 30 degrees or more to ensure that we can not only make the weld adequately with good quality, but also get it inspected. Think about also putting these members all together. So when we put them together, we have to make cuts in order to make sure that they fit. The fabricator has to cut them. We can't always have a perfectly square cut. Unfortunately, most things don't always go together that way for HSS. So you may have something like you see for these two diagonal branches here where we've got kind of cuts at 45 degrees. For rectangular sections, it's not the biggest deal. It's much easier to make those and at a certain angle and put all of this fit up of this particular joint can be put together. But think about a similar situation that we've got here where we're trying to make the cuts on these round. So this particular example that I show isn't so bad, right? We've got a very large tube that we're connecting smaller branches to. So while it's not going to be a square cut, there is some profiling that needs to occur for, to put all of these pieces together. But if you think about something like this, where maybe we've got a 10-inch OD branch member coming into a 10-inch OD cord member, where they're kind of a quote-unquote match type connection for rounds, there's a significant amount of profiling that needs to go into the cutting of these round sections. Historically, that's been done by paper templates and then cutting it by hand. More often than not, there have been some advances, or more often now, there have been some advances in laser technology and tube lasers, which is what you see here in this picture. What I want to impress upon you is that this is now another piece of of equipment. And you can imagine that this, using round members, is likely to be going to be more expensive in fabrication rather than the square members that are a little bit easier to cut. Some of the technology that's available here is this Vernon tool offered by Lincoln Electric. So this is an industrial pipe cutting and CNC pipe profiling machine, which you can see the different types of cuts that are applicable or that machine can perform. That 90-degree saddle is very much like what we were looking at in the previous slide, where the welding is actually taking place. But think about something also like this 45-degree lateral. So this is maybe something like a branch member coming in at a 45-degree angle to another round member. So we've got a lot of complex profiling that needs to occur in order to get that fit up just right. Obviously, you can see the benefits to using a tube laser for that cutting to get that connection put together adequately. Another thing to think about, rounds versus rectangulars, is actually putting this together. So we talked about the differences between rectangular sections and round sections in cutting in the previous two slides. Now let's actually put these pieces together. So here you can see, you know, we've got two verticals. We'll assume that this is a continuous cord member, and now we need to add another branch member kind of in the middle. So again, this is going to have square cuts at each end, and you can just kind of slide it into place very easily, right? With the square cut, it can be slid into place. And then if we've got some branches coming in also, or some diagonals coming in at 45 degrees or whatever the exact angle is, again, those are going to have kind of those square cuts, but at an angle. But again, it can be just kind of slid into place, and it's all going to fit, and then can be welded from there. But let's think about that for the case of a round HSS truss. So again, with the same starting point where we've got two cords and two branches, like a T connection. If we want to add an additional branch in between the two, these guys, how do we get this into place? We actually have to splice this member in order to just get it into place, right? We put each half in and then splice the piece together to be able to install it. Then if we've got some of the diagonals like we had in the previous, how do we get this guy in now? Because of that rounded member, we can't slide it in. The ends have to be profiled in order to make the welds. So it's very difficult to fabricate something out of round HSS like this. There are fabricators that are very good at it and do a great job of it, and it can be done. I'm not saying that it can't be done. These are just some of the factors for you to think about as you're selecting your members and sitting with your designers, that it might be a more economical option to fabricate based off of rectangular sections. All right, a little bit about weld effective length. So going back to what we were talking about for welding across the face of an HSS, where we started that in I think the first slide of the presentation. If we're designing to resist the actual loads, as I mentioned, we're going to spend most of the time today talking about, we have to account for the non-uniformity of the load itself, of the stress in the weld. As we mentioned earlier, the HSS wall is stiffest at its ends, closest to the sidewalls, and it's lowest in the center. The weld could unzip with cracking. That's going to start at the extremity, so on the outside. So for transverse elements, we need to use an effective width when we're designing parallel to, transverse to the longitudinal axis of the member. Even though the full weld isn't effective, like we don't use the full length in our calculations because it's not effective, a continuous weld is still required. I want to make sure that that's clear, that still does need to be employed. For elements that are parallel to the longitudinal axis of a member, like you can see in the lower graphic, those are considered fully effective. So as long as it's parallel to the longitudinal length of the member, those are fully effective. the development of the effective properties of a weld when you're designing these welds used to be in the specification and has recently been removed, but you can still find them through STI, the newer version of Design Guide 24 that's not out yet, that is coming, and also the 2022 specification has added those back into the commentary. So if you're looking for the development of those specific properties for your weld design, they can still be found in some other locations. When we talk about rounding or welding to round HSS, these AWS D11 clause 10.5.5 gives axially loaded round HSS have an effective weld length of, the factor is Q sub Z, which is essentially 2/3 of the total weld length. The branch welds are most highly loaded at the saddle points, as you can see in the diagram on the right-hand side. Conversely, the branch welds are most lightly loaded at the crown points, with branch stress sometimes even being in the opposite sense of the branch load. So that implied 2/3 of the total length is what we had to go by previously, and this would apply to a transverse plate to a round HSS or round HS to a round HSS. Isn't always super clear. So a great addition to the 2022 specification, which will be out later this year, is the addition of these effective weld properties for connections to round HSS. So this is new in 2022. It's not in the specification right now. As I mentioned, it'll be out a little bit later. This is based on some research done by Dr. Packer and Kyle Toussaint at the University of Toronto. You can look up their technical papers if you wish to see the background behind that, but this will be employed in the specification going forth. Another thing to think about is if we're welding round HSS to round HSS, we know we want to try and stay with a fillet weld because we know that those are most economical. But it's likely going to be difficult to obtain the full fillet weld throat thickness. The dihedral angle of the joint needs to be maintained. This likely can only happen with a fillet weld if you've got a small beta, so a small ratio of the dimensions from the branch member to the cord member. So that dihedral angle needs to be maintained as between 60 and 120 degrees, which is kind of difficult. There's also in D11 in this figure 10.5, there's this note 4 here that talks about if the angle is less than 60 degrees, then the Z-loss values in the table in D11 need to be applied for fillet welds, even though they typically only apply to PJP welds. So to keep the dihedral angle between 60 degrees and 120 degrees, there's a complex effect of the betas and the dihedral angles, which is just going to change continuously around the joint as you go. So it's complicated, but definitely needs to be considered. So it's not a slam dunk to assume that you can get a fillet weld here. There's a decent amount of work on the fabricator's part that needs to be done. I'm going to turn it back to Kathleen for a polling question.
Thanks, Kim. So we've come to our first polling question of today's webinar, and the question is, you might need to minimize your full screens to see the polling question. The question is, HSS connection capacity is most closely tied to what parameter? Length of the cord member, angle of the attached branch member, cord member thickness, or welding process type? So I'll give everybody a couple seconds to answer this question. Okay, so the results are in. 0% chose the first option, which was length of the chord member. 11% chose angle of the attached branch member. 73% chose chord member thickness is the parameter that most closely ties to HSS connection capacity. And then 16% chose welding process type. So now I'll turn it back over to Kim to kind of discuss the results of that poll. Thank you.
You guys are awesome. That's great. And it's a little bit of a trick question because you're entirely correct that the angle and the welding process do come into play with a connection capacity. But going back to the screen where I put a ridiculous number of icons and red marks on the screen, it's the chord member thickness that is highly impactful when designing with or designing HSS connections. So yippee, thanks guys. All right, so let's move forward to a little bit more discussion on HSS Weld Design. Starting first with fillet welds. We love them. It's well known that these are the least expensive and the easiest welds to make. There are considerations for a 1.5 increase that we need to talk about coming up here. But again, as I mentioned earlier, I want to reiterate here, the biggest difference between HSS connections and those connections to open members like wide flange channels, angles, is that they have to be single-sided. We don't have access to both sides of a tube wall typically. And so the leg size can often exceed the HSS wall thickness. There has been some misuse of a particular spec item that I wanted to bring up just to clarify. This particular clause that I'm referencing here in D11 and also occurs in the AISC 360 specification talks about a limitation on the size of the weld that is applied to an edge of a member. The reason for that is that you might melt away the top edge of a member. So you would result in a normal weld toe, but the corresponding weld throat thickness is much smaller than what you intended if you melt away the top edge of that member. And so the provision states that the maximum fillet weld should be the thickness of the member minus 1/16 of an inch. And the reason for that is so that you can confirm that the edge is not melted and the proper throat thickness is achieved. When we're talking about HSS to base plates, these are not an edge. So this particular provision does not apply I would say almost always to HSS connections. This does not apply. The directional strength increase factor has been in the specification for many years. It's based on research on lap slice connections that are loaded in shear. And then there was some additional research done recently that brought it into question. So this is what the specification states, is that we can increase the strength of a weld by a factor that ranges from 1 to 1.5 for fillet welds where strain compatibility of the various weld elements is considered. Going forward, what we've found is that single-sided welds to an HSS wall specifically, although I think it's pertinent to think about single-sided welds this way in general, but specific to HSS because we're almost always dealing with single-sided welds. When they're in tension, these welds are partially restrained, and you can induce some bending about the local axis leading to an opening in the weld root, as you can see in the diagrams on the right-hand side. When we do this, we see that the actual failure plane is closer to the HSS fusion face and has a longer failure line. So it's conservative to use the weld effective throat thickness as defined in the specification for this particular weld. The restraint that's provided to the fillet weld is going to depend on the HSS wall thickness as well as the shape, the weld size, and the penetration. So The effect of this of this bending about the weld root is much more severe on rectangles than it is in rounds. I think you can kind of envision that a weld that is round in shape is going to have more restraint to it than something that is along the face of a rectangular HSS, which is more linear. Therefore, the research supported this theory and found that the directional strength, or the 1.5 increase, doesn't result in an adequate safety factor that's outlined by the specification, and so therefore it's in the upcoming specification. In the previous specification, it was implied. In the upcoming specification, it's very clear cut that 1.5 increase cannot be applied to rectangular HSS that are in tension. It can be applied to round HSS that are in tension. It can be applied for double-sided fillet welds. Like if I'm welding a plate to an HSS, whether it's round or rectangular, as long as I'm welding it on both sides, like in a single plate connection, then it can be used if in tension. And obviously can be used, cannot be used for the effective lengths that are given in K5. So a little bit of clarification on when and where you can use that 1.5 strength increase. When it comes to fillet weld design, there's a table like this. It's in Design Guide 24 and is updated in the newer version of this, but we also need to check the weld metal and the base metal for shear when we're welding to HSS. A500, all the material out there in the marketplace is all grade C or dual graded B/C. So this table is much easier, especially if you consider just ignoring A53, which I hope everybody is not using A53 for their design. So if we just look at A500 grade C or 1085, depending on which one you're using, you know that base metal rupture is always going to control. So it kind of simplifies our weld design going forward, which is nice. There is a rule of thumb that in the past I've been asked about that I wanted to bring up here and provide some clarification to. There was a rule of thumb that a fillet weld that's equal to 1.1 times the thickness of the branch, it will develop the yield strength of the branch member. You can find that in the specification commentary in K5. You can also see it referred to in the Steel Construction Manual in Part 8. That originates from some work done and published in IIW in 2009 and also in the Euro Code 3. Recently, this has been confirmed for rounds, so it still can be a rule of thumb that you may use for rounds. However, for rectangular sections, it actually looks like that factor should be more like 1.3 rather than 1.1. So that hasn't been, this is just a rule of thumb, it's not codified, but if you are using this rule of thumb or have used it in the past, that's something you might want to take a look at and confirm if you're using that rule of thumb for rectangular sections. Again, hopefully we're not developing the yield strength of a branch member on a regular basis. We're designing for the actual applied loads. PJP welds are something that I hope we can employ more often, as they can be a much more economical solution rather going straight from a large fillet weld to a complete joint penetration weld. CJPs require backing, specially qualified welders, so it's a reasonable consideration to look at partial joint penetration welds. Welding full thickness for HSS is just complicated. The effective throat for those PJP welds is given in the specification in table J 2.1. Obviously, we don't often use or don't know what welding process exactly is going to be used. So it's really best that you specify the effective throat that you're using for your design. Rather than specifying anything else, just put that E in parentheses in your weld symbol, and then the fabricator has the ability to figure out the rest and do it how it's most economically for them. Much like the single-sided fillet weld discussion that we had previously, you should also ensure that rotation about the root of a partial joint penetration weld can't occur. Another option, if a partial joint penetration weld is not quite enough, again, to try and avoid going to that complete joint penetration weld, we can reinforce a PJP. That's definitely an economical option. The capacity of that reinforced weld does not equal the sum of the individual capacities. Again, we should specify an effective throat, which will be the least dimension from the weld root. And those are kind of given by these great diagrams that I know are probably a little bit difficult to see on the screen, but can easily be found in D11 in figure 4.2 through 4.4. The important thing here is that we need to be considering the Z loss at the root for the 45-degree bevels as well when designing these. Flare bevel and flare V groove welds are very common in HSS because of that corner. If we're welding to the corner of a tube, we talked about those when we're talking about matched connections. So the actual corner dimension, as I mentioned, was 2T on average, 2 times the thickness of the tube on average, but it's going to vary in size from mill to mill. Every HSS producer is likely going to have a slightly different corner radius. The effective throat is a function of that, though. It's given in the specification in table J2.2 and in D11 also. This gap that you see in that picture on the bottom left there at the weld root is common because that we can't get the full penetration, and that's accounted for in the Z loss calculations. These assumes a filled flush to the outside of the HSS, and as I mentioned, it does take into account the typical Z loss at the root and a typical HSS radius. But these numbers that are given here in this table, in this specification, what I want to impress upon you is that these are maximum. So a filled flush is not necessarily what we need to have everywhere. This is definitely a case where if you don't need it to be filled flush and on every single case, please put the effective throat that you do need in the weld symbol, and then that will allow the fabricator to design accordingly. I have a fear that we put this weld symbol on all of our drawings when we don't necessarily need it, and it results in a lot more welding than we actually need for that joint, and we might be able to save some economies by actually specifying what is required. An underfilled joint is okay and can save money. D11 requires of us as designers to specify the effective throat for the PJP weld. I don't think we always do that. I know that I'm likely guilty of not always specifying it, but it is required. Varying corner radii on the square tubing affects the amount of weld that is required, but these unfilled edges are okay as long as the effective throat is achieved. So what you see in diagram B there is perfectly acceptable as long as the effective throat that we've specified on our drawings achieves what we were looking for design. The one exception to that is for architecturally exposed structural steel. The Code of Standard Practice does say that underfilled joints for flare bevel groove welds or flare V groove welds, they do have to be filled flush. So that's the one exception there for that AESS category. I often look through the forum that AWS puts forth to find, to see what questions are being asked. This is one particular example of exactly what we were talking about, where someone was asking if this underfilled joint is acceptable, And obviously the answer is yes, and you can see how they're actually measuring that effective throat of the tube there, or at the weld, apologies. Just like partial joint penetration, welds may add some reinforcing. We can also add reinforcing to a flare bevel groove weld if we're welding to, let's say there's a plate that's being welded to the corner. If we have like a flare V groove weld where we're welding two HSS together, then that's much more difficult to add any reinforcing. But if we've got that face where we can land that fillet weld that's acting as reinforcing, that's definitely an option and another way of strengthening to achieve a weld that may be more economical than having to go to a CJP weld. I mentioned earlier, early on in the presentation, these match connections and the trouble that it can lead to. It's really impactful for the larger, thicker tubes as the radius gets larger for these thicker tubes. Then making those match connections or those flare bevel groove welds are difficult. The root gap is limited to a 16-inch as detailed and an 1/8 inch as fit up. Prescribed by D11. So if it's not, then it can't be pre-qualified. So then you end up with having to perform additional work. And there are kind of 3 different options that the fabricator may have to incur. The one on the left is tube profiling. So we talked about the cutting of rectangular sections and how it's pretty easy to make a straight, flat cut. Here's an exception though. We might have to profile a rectangular section so that these side walls that are longitudinal to the cord member are longer than the ones going across the transverse face of the tube in order to be able to make that weld with the appropriate root gap. Another option would be providing weld backing or building up the weld to provide that backing in the joint. And then the third option is, do we have to provide steel backing? So we get into a situation where we're looking a lot like a complete joint penetration weld, and we have to provide backing in order to minimize that root gap. A CJP weld should be the exception rather than the rule. There's a lot of work that goes into these guys. The backing is complicated. The backing can't be removed. So it's something that we need to try never to specify. I would argue that if you have to have a CJP weld, maybe this is something that's a good place for a casting. There are many casting manufacturers that have off-the-shelf castings that may be a good application for what you're looking at if you're looking at having to do a repetitive number of CJP welds. The backup weld at the root must be placed from the outside, obviously, which requires very precise root preparation. It's very fabrication intensive. If the specific weld can't be backed, it also requires a 6GR certification. So in the world that we live in the United States, if I'm trying to find a 6GR certified welder and I'm in Houston in the offshore, around the offshore industry where they do a lot of these welds and they're doing them in very large sections, it's probably not the end of the world and it's more easy to do. I sit today in Denver, Colorado, and I can tell you that it's very, very difficult to find a welder with a 6GR certification. It's the highest certification there is out there. It's very complex. It's very expensive and should definitely be avoided if at all possible. For the backing, if we're allowed to back the weld, and so we can use that, normally, I'm sure you're familiar that D11 says that the backing has to be continuous. We're trying to avoid stress risers in the backing by specifying that. However, in 2010, D11 allowed discontinuous backing for statically loaded HSS end connections. So that one application, you are allowed to have a discontinuity in the backing. It cannot be more than 2 pieces. So you can basically have 2 pieces that go inside and perform that backing. And the discontinuity has to be parallel to the primary stresses. So those are 2 provisions that have to be met if you're going to have discontinuity for your backing for an HSS at its end. As you know, backing can't be removed. Once it's in there after we've performed a weld, we can't really get in there to get it out. So mostly that's okay for statically loaded structures. In seismic, there are some cases where the backing must be removed. However, base plates is not one of them. You do not have to remove backing for base plates for seismically loaded HSS. For cyclically loaded structures, we're typically going to remove the transverse backing. And of course, for architecturally exposed CJP connections, any backing that is exposed to view has to be removed. Backing in general for rectangular sections is much easier to provide than round HSS. Round HSS are going to vary on the inside, obviously depending on the OD of the member, but also on the wall thickness. And so it's a little bit more difficult to provide that for a round HSS than it is for rectangular. When we're welding to HSS end to end, so if this is a column section and we're trying to transition from a thicker wall to a thinner wall, we need to again be cognizant of the fact that the bending radius of those corners is dependent on the thickness of the tube. It's also going to vary from producer to producer. So when you're calculating the amount of weld that you have or the amount of bearing that you have in something like that, you need to be cognizant of that. Some things need to be taken into account for welders that probably aren't that significantly different than what they're used to taking into account for normal fabrication processes. Distortion and shrinkage is going to happen. We've got to plan for it. Appropriate welding sequences have to be followed because they affect the shrinkage, the residual stresses, and the deformation of the welded structures, obviously. All of those factors come into play with that. Some ways to mitigate that is by using local heating. Preheating the member can help with that. And if you're working with a truss, starting from the center and working your way out may help to mitigate some of those issues. When it comes to HSS, more often than not, all position capability is required for HSS. When you're in the shop, rectangular shapes can often be positioned horizontally and then welded in the downward position. However, thinking about round shapes again, it's constantly rotating and that position is always going to change. Truss connections, we need to think about the access. So SMAW is going to provide great access, but is a slower method than gas shielded processes can using like a self-shielded flux core to arc welding will overcome that visually restricting that typically happens with the gas shielded processes. So the process comes into play, especially when dealing with truss connections. Here you can see just some examples of weld positions and sequences. The important thing to think about here, I think what's most significant is welds must never start or stop at corners that you can see here in the diagrams for the rectangular HSS. And then lastly, for architecturally exposed structural steel, welding is often the preferred connection as it's very clean. The location of a seam weld is significant. I've said before that I think that we as structural designers need to be specifying on that on our drawings because the fabricator is looking to us when most often they're usually not looking at the architectural drawings to put these structures together, and a seam weld is something that per the Code of Standard Practice for architecturally exposed structural steel needs to be oriented away from view, and my away from view and your away from view may be different perspectives. We talked a little bit about the flare bevel groove welds and the difference between underfilling and that for architecturally exposed they need to be required, and we also talked about exposed backing needs to be removed. I need to acknowledge two people that have greatly helped me throughout my career. I want to acknowledge Dr. Dwayne Miller as his impact on our industry is immeasurable. He's retiring after 42 years with Lincoln Electric, and I used his Design Guide 21 extensively in the illustrations for this presentation, so I want to thank him. And of course, Dr. Jeffrey Packer from the University of Toronto for always answering our questions and helping us with all things HSS. Some of the resources that you can use to further learn more about welding. Of course, you can always contact the Steel Tube Institute if you have specific questions about this presentation or anything outside of this scope. Anything related to HSS tube pipe, we're here to answer. Design Guide 21 is all about welding and available from AISC and is free to members. Design Guide 24 is in the process of being updated, and we should have that coming out fairly soon with the second edition. And there's an entire chapter that's dedicated to welding that will have extensive information. And of course, AWS D11, the 2020 version is what I used as the basis for this presentation. I'm going to pass this back to Kathleen real quickly. We've got an assessment question and then hopefully some Q&A from the attendees.
Thank you so much, Kim, for a great presentation. And I'll kick off. So this assessment question today is, let's see. Welders qualified to perform an unbacked complete joint penetration weld are common throughout the United States. True or false? And I think we all know the answer to this question based on today's presentation. Kim, would you like to speak to the answer? I'm happy to as well.
Yes, it's the answer is false. That 6GR welder certification is fairly uncommon throughout the United States, more common in the Gulf Coast where they do a lot of work for the oil companies, but it's very uncommon everywhere else.
Perfect. Thank you so much, Kim. And then moving on to our last polling question for the day. It's a simple one. You might need to minimize your screens to see it. Do you want a PDH certificate for today's webinar? So I'll give everyone time to answer that. Great. And now we can move on to questions for today. We have just a few minutes to answer any questions. So if anyone has questions, please feel free to enter them in your questions widget on the GoToWebinar control panel. And we do have two questions here that have come in. So the first question is, you mentioned that we can use the directionality factor for plates to HSS. That 1.5 factor can be applied as long as there is a weld on both sides of that plate. We would like to clarify if this is true for both longitudinal and transverse plates to HSS.
Yes, so remembering that this is for welds that are in tension, and if they are double-sided, so not single-sided, then the 1.5 factor can be used in general. Now, when that would only apply to anything that is, I would say, not given in K5. So a weld that is not fully effective is typically covered in K5, sorry, and it would not be, you would not be able to use the 1.5 factor there. We're already reducing the length of the weld that is effective. Remember when we're welding across or transverse to a tube, and we can't then bump it up by 1.5. We have to only use the effective length for that in order to meet the factors of safety.
Perfect, thank you. So we cannot use it for any transverse plates, right? Correct. Thanks, Kim. And the second question that we have are, what are your thoughts on showing the all-around weld to HSS connections in our design drawings. Is that good practice? Do you have any recommendations for that?
Yeah, it's a good question. I am a proponent of only putting what we need. So if I counted on the entire length of the footprint around an HSS in my calculations and I need that, then by all means, of course, I want to put the all around. The all around symbol to me feels a little bit like just putting the flare bevel symbol without an effective throat in it. It's likely overkill. Why not give the fabricator the option? Maybe they'll provide weld all around. Maybe if I just say that I need, weld on the flats of the four sides of the rectangular section, then if that's all I need, then that's what I think I would prefer to put, and leave that up to the fabricator to decide what's most economical for them, but not requiring more than what we really need.
Awesome. Thank you so much, Kim. So those are all the questions that we have for today, and we thank Kim Olson for kicking off our STI webinar series for 2022 in such a great way. And we hope everybody has a great rest of your day. Thank you so much.